I'm studying renewable energy in master degree in Qasim University. Today I will present my research about anaerobic co-digestion of DatePalm waste and co-manure to enhance biogas production using bench scale digesters. This work focuses on optimizing substrate combination to improve renewable energy generation from agricultural residues in arid regions. Globally, energy demand is increasing while concerning about fossil fuel depletion and climate change continue to grow. At the same time, large amount of agricultural waste are generated but remain underutilized. In Saudi Arabia, date palm waste is produced in significant quantities, yet it is often disposed of through burning or damping, leading to environmental pollution. This creates both a challenge and an opportunity for sustainable energy recovery. Date palm waste has a high lignin content and a very high carbon to nitrogen ratio, which makes it difficult to degrade biologically. As a result, it's a direct anaerobic digestion produce a low methane yields. On the other hand, co-manure contain beneficial microorganism and buffering capacity, but does not maximize energy output when used alone. Therefore, there is a need to determine an optimal combination of these substrates to increase digestion performance. The main objective of this study was to determine the optimal mixing ratio between co-manure and date palm waste. Specifically, we aim to enhance cumulative biogas production. This is our goal to produce biogas production, improving methane content, and compare co-digestion performance with monodigestion system. Here, the experiment here, as you see in the picture, was conducted using 5 identical bench scale cylindrical digesters. Each digester had a total volume of 4.5 liters and a working volume of 3.2 liters. The reactor were operated under mesophobic conditions, which maintains between the temperature of 31 to 35 degrees Celsius over a digestion period of around 64 days. Biogas production was measured using the water displacement method. Each reactor was connected to its own graduated cylinders. As gas was produced, it displaced water from the cylinder. The displaced water from all cylinders was collected in a shared water tank. For future improvement, separated water tank for each reactor are recommended to increase measurement accuracy. 5 different substrate mixtures were tested. These ranged from 10% date palm to 10% co-manure. The intermediate mixtures allowed us to evaluate how different proportions affect biogas productions. The key mixture of interest was 45 to 55 ratio of core manure to date palm waste. The digestion process was conducted under stable mesophobic conditions. The pH was maintained near neutral between 6.8 and 7.2. Importantly, daily shaking is very important. The daily shaking was performed to enhance the mixing. This improved contact between microorganism and substrate to increase digestion efficiency and biogas yield. This graph shows the cumulative biogas production over the 64 days digestion period. We can clearly observe that the co-digestion mixtures outperformed monodigestion. The E3 mixture consistently produce the highest cumulative biogas volume, as you see in the figure. The optimal mixtures was A3, consisting of 45% co-manure and 55% date palm waste. This mixture produced 52.5 liters of biogas. This represents a 28.4% increase compared to date palm waste alone, and a 15.6% increase compared to co-manure alone. Methane content is critical because it's determined the energy value of biogas. The optimal mixtures achieve the highest methane content at approximately 62%. This indicates improved conversion efficiency and high energy quality. The improved performance can be explained by several factors. First, co-digestion balance the carbon to nitrogen ratio, creating a more suitable environment for microbial growth. The second, co-manure provides buffering capacity, maintaining stable pH levels. Finally, the microbial synergy enhance the breakdown of complex organic materials. The modified Gompertz model was applied to describe the kinetic biogas production. The results showed an excellent fit with R squared values above 0.997. The optimal mixture also exhibited a shorted lag phase and a higher production rate. Statistical analysis confirmed that the differences in biogas production were significant. ANOVA results showed a p-value less than 0.001, and the post-hoc analysis indicated that the optimal mixtures produced significantly more biogas than all other treatments. This study demonstrates that agricultural waste can be converted into renewable energy efficiently. It produces environmental pollution and supports sustainable waste management. The findings are particularly relevant for regions with abundant date palm residues, such as Saudi Arabia. Several improvements can further enhance the system. These include the continuous or automated mixing, and also can be separate the gas measurement system for each reactor. A pressure monitor for safety. Also, if we use a pressure monitor for safety, this is improve the experiment, and operating in control temperature environmental. These improvements can increase accuracy, safety, and scalability. In conclusion, co-digestion significantly improved biogas production compared to monodigestion. The optimal mixing ratio was identified as 45 to 55 co-manure to date palm waste. The system operated stably under mesophytic conditions and produced high methane content. Further research should focus on scaling up the system to pilot or industrial levels. Economic analysis is also necessary to assess feasibilities. Additionally, continuous reactor systems should be evaluated to better simulate real-world applications. And thank you for your attention. I would be happy to take any question.